All right, so we are finally live now. And today, guys, it's an honor to have with us today Michael Bretti, an experienced electrical engineer and the founder of Applied Ion Systems. It's good to have you here.
Oh, thank you. Thank you for having me here. I'm very excited to be a part of this.
And I would also like to welcome all the audience that are joining us, and that will be and those who will be joining us today as we go through the questions. Right. So, the Applied Ion Systems, like it sounds really something like big sci-fi stuff, right? So just tell me about something about your company.
Well, applied ion systems actually first started out kind of completely as a hobby. Um, about 2 years ago, I decided to try and get more into high vacuum plasma physics in sciences. So I started up the Applied Ion System website just to share my projects and work in those areas. So I started building some vacuum chambers for a few different projects. And one of the projects that kind of came up was propulsion. I'd always been interested in propulsion, especially plasma and ion thrusters. And I thought, hey, it'd be kind of cool to try to just do this stuff on the side and play around with it a little bit. So I started doing that, and as I shared my work more with the community, with just the maker community on Twitter and online and everything, more people became interested and encouraging in that direction. And I got introduced into the nanosatellite community, specifically the Pocket Cube community, which are 5 centimeter cube satellites. And I found out there was a real need for propulsion at that scale. Nobody was really working on it, and there's nothing out there available for these small craft. So I decided to transition fully into exploring and developing propulsion for these types of systems. And eventually, as I got more encouragement and following, and started developing actual deployable systems, I kind of turned it into a more of an official company to be able to collaborate and develop more easily with others around the world.
All right, so Mr. Michael, like I saw on your LinkedIn profile that you are actually an experienced electrical engineer, like concentrated on electronics, and then you switched on to this plasma and ion stuff. So I just wanted to know, like, how difficult was it for you to switch from engineering background to completely science background?
Well, I never actually fully switched to a completely science background. I've always been interested in plasma and high vacuum and particle beam physics. That stuff I've always explored on my own. So I, never took any courses in undergrad for that. This was all self-study. Even the propulsion stuff, this is all stuff that I've learned myself and got through various areas of study. And it's so multidisciplinary that you can take a lot of things from a lot of different places and apply it. So really, transitioning into this was more of me embracing the areas that I've already really loved studying and actually started now applying more project-based.
Okay, cool. So yeah. So about like since you've come a long way, like after having established applied ion systems, uh, I want to know about your journey till here. Like, what have you done, and what are your future visions? Like, what are you actually planning up to?
Yeah, so actually last May, I achieved the very first ignition pulse from one of my thrusters. It was actually the second thruster I built. And actually have them here to show the audience now. So this was the very first thruster I actually ever built. It's a pulse plasma thruster. So very simple design. It has actually pretty modular build. So there's the socket here for the anode, the cathode, and the igniter. And then there's the actual thruster here itself. So the Teflon fuel in the center and the stainless steel electrodes that all plugs in. This one never worked, but sharing this with the community actually got me introduced to the nanosatellite community in particular. And I started working on designing systems more usable for that size craft. So the very first thruster I actually worked on, called the GPPT-1. This is also a pulse plasma thruster, but a very unusual style. It's a very flat um, type, which was to work with the space constraints of the pocket cubes. So this one actually only fired once. There's videos on my website and on YouTube I've uploaded of this thing firing, but this was kind of the very first starting point of all my projects going forward. Showing that I could actually achieve, an electric propulsion thruster operating in vacuum at home. So moving on, I shrunk it down further. So we have here the GPPT2. So all it is, and again, on my website, I actually have all the CAD models, all of the information, everything, build pictures, and in the entire process, which you can actually go through, download, and see how this is put together. I have test reports. So everything available for anyone to actually look at this stuff and actually see how it works and get involved. So this thruster actually fired quite a few times successfully. I was able to actually measure the thrust and the impulse bit with it, so I could actually start looking at optimizing the design a bit. Moving forward in October, I was actually contacted by a Pocket Cube group in Spain, the AMSAT Spain group, and they approached me asking if they could fly some of my thrusters. So I had a couple of months to actually get a system built, tested, and sent out to them for integration, because they were looking to integrate and start working on integration in December. So this is actually the result of the thruster. So you can see here, this is one of the iterations. This is the GPPT3. So this has all of the control, all the low voltage, all the high voltage, the thruster, the fuel, everything on it. It's very compact, 40 by 38 millimeters, by I think around 25 millimeters or so. So this was actually put on the satellites now, and those will actually be launched this July. So 2 of these thrusters will actually be going to space this July, tested aboard the AMSAT Genesis N and Genesis L pocket cubes. So that'll be a very exciting thing for the community, because it'll be really the first time that I know of that, home-built thrusters. I literally built them at home in my, on a desk in my bedroom, and sent them over. Really the first time that an open source home-built thruster will actually be launched and tested into space. So that'll be very exciting for the community. And going forward, I'm working on some much more advanced technologies. The new thruster that I'm working on that is very, very hyped now because of the high thrust to power ratio and very high ISP, is the ILIS-1. So this is an ionic liquid ion source electrospray thruster. So you can start to see that I actually started putting together the preliminary assembly. So this one, unlike the other ones that I showed, which are plasma thrusters, this particular thruster is an ion thruster. And it's very unique because it uses room temperature molten salt fuel that are held inside of porous glass structures. So it has, it uses capillary action to feed it. So there's no valving, there's no pressurization. It's just all passive feeding. And it's very, very low power, very ideal for scaling. So that technology is very exciting for nanosatellites, and I'm working on ways making it very, very cheap and much more accessible for the community. The testing for that, actually, I'm gearing up for the test quite literally in 2 weeks. So that will be the first ignition test of this particular thruster. So I will be live tweeting that test as well. I'll probably have a live stream up on YouTube showing the thruster firing and operating. And if that works, I'll be, talking with some other groups that we're going to be launching this possibly by the end of the year or early next year. So already working on launch for these new thrusters. So going forward, there's going to be a lot of excitement working on this new ion thruster technology and getting that ready for launch.
So that's amazing. Like, I guess there's a lot of things stacked up for the coming future, right? So I wish you the very best of luck. And you're talking about the thrusters that you told us, right? Like, what is the maximum thrust you have achieved till now?
Right now, for for these types of thrusters, really for electric propulsion in general, the biggest constraint is power. That's going to dictate, the ultimate performance and really what type of technology you can actually run. Um, for this type of thruster, I had about half a watt of total power to work with. For the pulse plasma thruster, I had about half a watt. So there's very, very little power available for me to actually do much with. So when I measured the thrust on that, for the integrated system, I achieved about 0.22 micronewtons of thrust. So less than a micronewton of thrust, so really, really tiny amounts. For higher altitudes, you could actually do some stuff with that. But for the lower altitude we're launching at, about 300 kilometers, there isn't much thrust besides having it being a tech demo. But going forward, like I mentioned with the new Illis 1, so the new electrospray thruster, this one is going to be rated at about 1.6 watts max power. So the thrust densities that I'm looking at for that are on the order of around 14 micronewtons per watt. So I'm anticipating, based on scaling and projections and looking at stuff in the literature, that this new ion thruster will be able to achieve about 22 micronewtons of thrust. So 100 times more than the previous thruster with only 3 times as much power. And at that level, for nanosatellites in low Earth orbit, you can actually do quite a lot. I have some graphs and posts and stuff that I did showing the correlation between satellite size and altitude and the different thrust levels and what you can achieve for station keeping. And even at low Earth orbit for these small satellites like pocket cubes and CubeSats, you only need 10 micronewtons of thrust or so, 10, 20 micronewtons of thrust to actually do orbit keeping. So although electric propulsion offers a lot of times very low thrust, when you're actually in space, you don't really need that much thrust to do station keeping or maneuvers. It takes a lot more time than chemical propulsion, but due to the higher efficiency, you can operate longer with less fuel.
Okay, so talking about the testing, how do you test these thrusters?
Yeah, so I actually designed and built my own high vacuum chamber system. So that's actually currently in the basement. And one of the great things are there's a very wide do-it-yourself high vacuum community around the world. So people all around the world in the amateur community are building their own vacuum systems for high vacuum physics. There's plasma, there's neutron production, there's homemade semiconductors. And what I've really embraced, which really no one has really started doing yet, is electric propulsion. So this is a very small chamber. It's actually, I have some stuff here now that I'm currently setting up for my new test. So this is a high vacuum flange with feed throughs. So you can see here, there's the feed throughs and wires. This was from the old test that I'm going to start cleaning up and prepping for the new system. So this is actually the internal size of the chamber. So it's a very, very small chamber. And what I can do is since it's so small, it's much cheaper, it's easier to work with, and I don't really need much space. A lot of times when you see electric propulsion companies, they have chambers as big you can walk into. But for micro propulsion at this size, you can really get away with little. So a year before I actually started doing all this, I spent time really becoming an expert in high vacuum engineering. And on my website, I actually have all the designs for all the high vacuum systems I designed and built. So you can get the CAD models, you can get thermal simulations. I have simulation files. There's a high vacuum simulation software from CERN that's free to use and very powerful called MoFlow. I have the files for that and the walkthrough to actually go through how you design and use that system. So there's a lot of great resources out there, and there's several communities also that openly talk about high vacuum that I'm also involved with. Um, so that's really the testing setup. So I have the chamber down in the basement. I have control system with Arduino, basic water cooling, the high vacuum pumps. So it's a very homemade setup, but it works very well for this purpose.
So actually, Mr. Michael, like while you're testing out your thrusters, right? Heating might be a really big problem to the thrusters. So how do you solve that problem?
I'm sorry, could you repeat that?
Like when you while you're testing your thrusters, right? Then they actually tend to develop a large amount of heat that dissipate large amount of heat. So how do you solve that problem of heat losses?
Actually, for the size thrusters that I'm working with, heat's not an issue. If I were to be doing more continuous discharge thrusters, like Hall effect thrusters that have a discharge chamber that's constantly sustaining a plasma in a ceramic liner, heat would definitely be an issue. But for pulse plasma thrusters, there's almost no heat generated because it's a very brief pulse. The pulse happens on the order of a few microseconds, once every few seconds. So it's very low. And even for the new electrospray thruster, the process is completely cold because the ions are actually extracted from little Taylor cones or cones of liquid that form from the pores of the emitter. So it's a very cold process. Going forward, I do actually have a few designs. There's a new IO series, I'm calling it, that I'm working on. It's going to comprise of two thrusters, a gridded ion thruster and an RF plasma thruster. So those ones actually will have heat that will have to be dealt with because those will be more continuous discharge because they have the plasma discharge chamber, and either the plasma is getting accelerated itself, like in the plasma thruster, or for the gridded ion thruster, the ions are being extracted from the bulk plasma. So that one will be very interesting. That'll be a much larger system, about 50 to 100 watts, as opposed to the couple watts that I'm working with now. And that will also be using solid iodine fuel. So it'll have a heater to vaporize the iodine and everything. So it'll definitely be new territory for me going forward. So we'll have to see how that goes. I'm not sure how I'm going to deal with the heat issues yet. So we'll see.
Okay, so like since you've for the last 2 years you've been doing like a lot of projects, you've been building these thrusters. So I just wanted to know like what has been the most challenging phase. Like you might have come across some sort of problem, right? So like I would really love to know about it.
So definitely, I think one of the most challenging things has been actually taking these thrusters and really scaling them down to the class that I'm aiming to operate at. So the pocket cube scale class, because again, while there are a couple of universities that have played around with pocket cube scale thrusters, there's really almost nothing in literature. All they go down to is really CubeSat scale. So it's been a real challenge actually getting these things smaller and working at very low power levels. Like for the pulse plasma thruster, the biggest challenge was size, figuring out a way to make it compact. And I spent a long time before I came to the flat stacks topology to get that all to fit. And for the electrospray, there's a lot of challenges with that. Normally for electrospray, the conventional way for these types of ones called ILIS, or the ionic liquid ion source, these are fabricated with many microscopic needle emitters on a glass surface. So these are laser ablation machined, which obviously I have no way of doing myself at home. But recently, in the past few years, there's been research on normal CNC machined emitters. Um, so I've actually gotten some emitters, just regularly CNC fabricated from a glass CNC place. So these are much larger, and they use actually standard chemistry filter glass. So it reduces the cost and complexity quite significantly. But then going forward from that, um, even more challenging was the electronics, because that thruster actually operates on both plus and minus voltages. One thing that's unique about it is, unlike conventional ion thrusters, this one you can extract both positive and negative ions from the fuel. So in order to do that, you flip the polarity on the thruster. So this one operates up to plus or minus 3.5 kV. So you can imagine switching, plus and minus 3,000 volts on such a tiny board is quite a big challenge. And the switching technology was a huge hurdle to overcome. Finally, so I actually have one of the test modules here. So this has the electronics on it currently, and you can see right here, this little black piece on the side, that's actually a micro high voltage relay. So that is rated for 3.5 kV or so, but only 1 kV switching. So what I had to do to overcome that was control the power supplies and the relays separately. So that ways the relays are always on before the power supplies are switched on. And by timing the control properly, I can get within the switching specifications of the components. So getting everything really compact into that tiny size has been a massive challenge. And just in general, scaling for electric propulsion is one of the big challenges just in the field. So going smaller is much harder than going larger. And I decided to start with the smallest size possible, Pocket Cube, because, overcoming those challenges, if I were to scale up to a CubeSat size one, for example, like the electrospray thruster, that can be scaled up simply by paralleling a bunch of modules for higher thrust. So, going up to a CubeSat scale, that's much, much easier. I mean, you have so much more space, so much more power. So it's become much easier in terms of scaling. But definitely there's a lot of technical challenges in getting these tiny thrusters down to this size.
Um, unmute, please. Yeah. So actually, there's an interesting question put forward by the audience. Even I was looking for the answer to this question. How do you name the thrusters?
Yeah, so I've always been horrible at naming stuff. Um, just my whole life, just I've never been able to name things well. So I kind of work on acronyms based on um, what's kind of related to the technology. So for the GPPT, like the GPPT series, I kind of named that like for gridded pulse plasma thruster, because the very first one um, is a grid of holes. For the illest one, that was fairly easy. That was ionic liquid ion source. For the IO series, it's IO for iodine. So not the most creative stuff, but it works for now.
Names are simple, and like I like it's good to have like such simple names, right? So like about the process of building this technology, like is there a specific roadmap that you follow?
Uh, well, everything that I do really starts with the fundamental question, which this is how I've always approached engineering, even way back in high school and earlier. Whenever I see something cool that I want to try myself, is how do I build this at home myself with little to no resources? And forcing myself into the mentality of, there's this advanced technology. What ways are there to simplify it so that ways I can experiment with it myself? Um, so going from there, everything starts with just simple paper sketches, and then I do a very deep dive um, into the technology across the board. So I look at any papers associated with it in academia. I look at industrial systems, so either full products or stuff that's out there, and then really branching out, looking at all the different related technologies. One thing about electric propulsion in general is that it's very multidisciplinary. I mean, it takes things from ion beam physics, electron beam physics, just particle physics in general, high voltage, mechanical, thermal, microfluidics, plasma. So there's a whole bunch of fields that go into this. And a lot of the thrusters, really every thruster technology you see is derived from something else in industry. Like RF plasma thrusters, for example, are really just inductively coupled plasma torches that are reconfigured kind of to operate as thrusters. Ion thrusters are kind of specialized ion guns and particle accelerators. Like neutralizers for these types of things are specialized electron guns. Electrospray stuff, the basic principles of that can be found in printing. So inkjet printing, there's stuff in chemistry for electrospray and certain manufacturing technologies for electrospray deposition and everything. So all these technologies are rooted in some prior industrial process or technology, and you can actually take the principles and the basic physics of those and apply it. And I've found that looking just beyond the thruster technology itself and exploring everything related really helps you come up with new ways to do stuff. And often a lot of the solutions that I've found have been kind of branching to other related areas and kind of picking things. Like for the electrospray thruster, I came across the CNC manufacturing method purely by chance, and that was through a lot of exploring and just looking at related topics in the area. So I think broadening a lot of what I do is looking far beyond just the individual technology itself and looking at related fields. And then once I have all my research there, then I start working on ways to accommodate the limitations that I have. So the power constraints, the size constraints. I always look for using as few custom parts as I can. So all the electronics I can buy off common suppliers like DigiKey or Mauser, hardware supplies off online hardware suppliers. So I try to minimize the manufacturing as much as possible, just so that way is, it's cheaper for me to do it, but that way is when I post this stuff and show people how it's done, other people can actually explore it more readily.
Oh, that's really amazing. Like having things, all of the things being just built at home is quite. It's really interesting to know like how you build these systems right at your home. Even where we've got people in the comments, they are saying the same thing. They really love your way how you're developing all these advanced systems at your home. That's really amazing. Okay, so there's this question put forward by Mr. Sunny Kabrawal. He wants to know. He says that he has got no knowledge of rocket engineering and he wants to learn about ion propulsion. So how should he start?
Well, there's already a lot of really great resources on ion propulsion systems. There's a fantastic book that's available from NASA on the web. I think it's called the Fundamentals of Hall and Ion Thrusters by Goebel and Katz, and that's a really great book to start with. That's where I went for a lot of the equations for looking at the new ion thruster I'm building for thrust and ISP, and that's a great overall book. But there's a lot of resources, just general resources online for the ion propulsion, and a lot of things that I do actually. When I'm looking at learning these technologies is even going to Google Images and typing it in. When I read a paper and stuff, the first thing I do is I look for all the figures, the images, and everything, because I'm a very visual, hands-on learner. So for me, I like obtaining information through kind of things that are related to the builds. So even just looking at these systems and seeing how the general overview and how they're built and the different parts of it can give a lot of information. So I would say there's definitely a lot of resources for getting involved with ion thrusters, and even in general, like I said, all the physics of ion thrusters are, general ion beam optics and everything. So you can also look at areas for ion guns and general particle physics and get some of the ideas related to that stuff as well. It's a little bit modified for making an ion thruster, but again, all the physics apply there. So there's a lot of different ways to actually approach this.
I mean, even I'm reading a paper, right? Because as of now, I'm currently an intern at a Department of Space Tech and Rocketry at BITMESA. So, like, I'm currently working on atomization. So, even my professor suggested me a research paper to read. And honestly, like, I'm going to try this method of yours when you told me that you go through all the visuals. Because honestly, every time I go for reading that paper, it's something really. There are lots of things that I cannot comprehend, right? So I'm definitely going to try this method once.
Yeah, and definitely like looking at like keywords related to the technology and looking at stuff like that. So even if it's not directly applied to atomizers, for example, but it's something related to just the general topic. Branching out and looking at other areas and seeing how these technologies are applied to other things can be very helpful.
Exactly. So, okay, so there's this question put forward by Mr. Diego Garcia Cacho. I guess that's how it's pronounced. I'm sorry if I pronounced your name wrongly. He asks, he's asking your thoughts on RF thrusters and Vasimir thruster, VASIMIR. I don't know
Uh,
what that is.
Yeah, so for RF thrusters, for every electric propulsion system, there's obviously a lot of strengths and weaknesses involved, and really is when you're selecting thrusters, it's very mission specific. RF thrusters are very nice because you don't have grid erosion like traditional gridded thrusters. They're mechanically much simpler. Again, they're just inductively coupled plasma torches. If you look at the RF thruster that I'm designing now, um, I'm literally using a 3D printed shell with a simple wire coil embedded into it, and then a ceramic tube that inserts to protect it from the plasma. So if you can get RF and you can put fuel through that, RF antenna, you've got yourself essentially a plasma source for a RF thruster. So RF thrusters generally operate at lower ISP than traditional ion thrusters, but they can achieve reasonably good thrust, and they're also very fuel agnostic. So really, you can throw any gas through it, and if you have the right power and good coupling, you can ionize it and use that as your fuel. So RF thrusters lend themselves very well to being able to use all different types of fuels. So that's another good advantage of these types of systems. Vasmir is a very interesting RF thruster because it's probably the biggest one out there that's being developed. I mean, this is like hundreds of kilowatts or megawatt scale class thruster. This is a really, really big high power RF thruster that's going to be explored probably eventually for human exploration. So it's a very interesting topic. I know there's been some debates on how well it would actually work and if it'll perform as well as the initial expected um, expected results. But overall, I think the technology itself, RF plasma thrusters, are just as valuable as ion thrusters or any of that stuff. It really depends again on the mission specs, and there's definitely just as many RF plasma thruster companies now as traditional electric propulsion companies. There's a lot more. There seems to actually be a lot more growing interest in RF plasma because you can deal with erosion a lot better and operate on a wide range of fuels. Like working with iodine because it's solid. It starts solid, so it makes fuel delivery much easier. There's a lot of interest in water vapor as a fuel. So there's a few companies working on water vapor based RF thrusters. So it lends itself really well to actually these alternative fuel technologies.
Okay, so Mr. Michael, I've got few more questions lined up, but before that, a really big thanks to Mr. Tejas Shenoy for having connected us to you. Right. Thanks a lot, Tejas Shenoy.
Oh yeah,
This was
thank you, Tejas. That was yeah. He reached out to me on Instagram, just questions in general about the electric propulsion, and I really appreciate that he actually reached out to you guys and then connected me. So thanks a bunch. This has been a great opportunity.
the best part of having a space community. People just keep on joining, right? That's amazing.
Yeah.
Yeah. So actually, I like when you showed all of those small thrusters, right? I see that there are no nozzles on the thrusters, right? So is it something like we don't require a nozzle for these thrusters, or is it just because they are small they don't need one?
So one of the things about electric propulsion in general, due to the physics of it, is that the exhaust velocity is extremely high due to the acceleration mechanisms. So chemical propulsion exhaust is limited um, based on the mechanisms of how it works. But for ion and plasma thrusters, the exhaust velocity is many times higher. So for an ion thruster, uh, you don't need a nozzle really doesn't do anything. For plasma thrusters, actually, you can and they are implemented. You can take advantage of magnetic nozzles. So instead of a physical nozzle, the magnetic field actually works on the plasma to constrict and accelerate it, and works actually as a converging diverging nozzle itself. Um, and actually, in the pulse plasma thruster, the newest one, and if you see the pictures of the build on the website and other areas, that one actually has an embedded magnetic nozzle in it. So there's a tiny little ring magnet inside the anode that acts kind of as a nozzle. So for electric propulsion, there are a few technologies that do benefit from nozzles. Resistojets, because you're using heat, electrical heat to further expand and accelerate the gas. So that always uses nozzles. And then again, for the plasma thrusters, for electrothermal plasma thrusters, you can utilize magnetic nozzles. Because with a physical nozzle, you're going to have the plasma hitting the sides and eroding it. Whereas a magnetic nozzle, you can keep the plasma away from the actual physical sides and structure to help limit erosion. So the nozzles are actually involved, just a little bit different from chemical sometimes.
Okay, that's really amazing. But okay, so yeah, this question is actually pretty interesting here, put forward by Srisha Madhu. They ask, how can we achieve thrust vectoring in ion propulsion without nozzle? Like, do
Yeah, so that's actually one of the benefits of ion optics is that you can actually use electric fields to change the convergence and the divergence of the beam, and you can also use like segmented electrodes to do beam steering. So there's actually a really great company out there, Propulsion, who's doing FEEP, which is field emission electric propulsion, which uses metal fuel liquid metal fuel that's wicked through porous tungsten emitters and emits either indium fuel, and there's another one, Morpheus Space, that does gallium fuel. But with the end pulsion one, what they actually have is a segmented electrode. So there's three quadrants on it, and by changing the proportion of electric fields in those quadrants, you can actually achieve steering of the beam electrostatically.
Okay, so I hope Srisha, your question was very well answered. So now coming to the space industry and the education sector, like these are the last questions that I'm left with now. So how do you think, like in so from revolutionizing point of view, how do you think the ion propulsion is going to help the space industry get a new shape?
I think it's already done a tremendous amount for the space industry in general. Again, there's so many new companies popping up doing electric propulsion because there is a lot of excitement for it, especially at the smaller CubeSat and Pocket Cube scales now. Um, just because, like for Pocket Cubes, for example, you can't launch with um, any pressurized fuel or anything. So that eliminates chemical completely. You can't launch with any pyrotechnics. So you're really only left with a few select electric propulsion technologies. And in general, electric propulsion has a lot of advantages that you have less fuel um, for a given mission, and depending on what you want to do for station keeping, you don't need huge amounts of thrust for basic maneuvers like object avoidance or collision avoidance or even deorbiting. You don't need tremendous amount of thrust. You can get away with very small thrust. So electric propulsion works very well for that. One of the issues with that and going forward in general for propulsion is that it's still extraordinarily expensive. Even for micro ion thrusters on the market, the starting price is around $50,000. So still, there's a lot of CubeSat and nanosat teams that can't afford this technology yet. So like what I'm doing is looking at making these systems more available at an order of magnitude reduced cost and simpler design. So that way, a lot of these university teams and starting teams can really start to explore this stuff. So definitely reducing cost is a key constraint going forward for propulsion, for electric propulsion. But it's already had a major impact on the field. And it's the first electric propulsion thrusters, I believe, actually flew sometime in the 60s or 70s or so decades ago. So they've already been very well researched for many decades. But going forward, the big push has been miniaturizing these systems to fit on the growing number of smaller and smaller satellites being launched.
All right. So Michael, actually, the thing is, like in our country, if you see the curriculum or the academics, right, we don't have a hardcore space related studies. Like you won't find any syllabus for that, right? So I don't know like about US, but the question is actually like, how do you think that the space education is actually going to help us set up the space culture in a country?
I mean, obviously, I think space education is very important, and it's definitely I think necessary for any country if they want to get more people first of all excited about space technologies, because if you're not offering those avenues for students to explore it, maybe people who would be interested in it wouldn't know that it actually existed. So I think it's very important, even from the standpoint of getting people excited and involved with it. And a lot of these, like in the U.S., tons and tons of um, colleges have CubeSat programs now. So it's a way to really get students some actual hands-on practical experience with working and designing these systems, and offers a lot of opportunities for graduate research and other research projects that are directly involved with space technologies. Um, so I think it's definitely very important to have these types of things. But even then, it really depends on how it's being approached. Like I my background is electrical engineering. I've never taken any space or propulsion classes. I'm completely self-trained in that area and with self-study. Um, so I think that the information is becoming more accessible in general. That if you really want to learn about it and have a passion for it, you can start doing it yourself now. Oh, did we lose Deepak again? I think his feed is down. So while he comes back on, um, I can go through some of the chat questions that were answered. If if you can't hear me or anything, or if the chat's not working, just let me know. So let's see. So Manev Patel asked earlier on, how much thrust can we achieve? So for electric propulsion, one of the trade-offs is efficiency versus thrust. So electric propulsion will always have much lower thrust than typical chemical propulsion. So usually in this range, you're looking at micronewtons to a few millinewtons of thrust for systems. And it depends on the type of technology. Some technologies will have higher thrust at lower efficiency, and there's always that trade-off between. But generally, when you're looking at ion and plasma thrusters in particular, on the order of millinewtons to a few micronewtons of thrust. Oh, AD back. I was just answering some of the
Yeah,
questions while you're.
yeah. Thanks for taking the control. So actually, there's this very favorite question. Like, I personally love this question, right? So the question is, what would you prefer? A safe up-down journey to ISS or a one-way trip to Mars?
Definitely at this point, a safe, guaranteed trip to the ISS. I'm already terrified of flying on planes as is, so I don't know. Going to Mars would be quite even to the ISS would be quite an ordeal for me. But there's a lot of the Mars colonization stuff would be really awesome to see, and I hope we achieve that. But I'm definitely not one for actually going there myself. There's a lot of stuff on Earth, really cool stuff that still like to contribute and explore here. So yeah, just a nice trip to there, just to be a part of that.
Okay, that's amazing. So, like here at Star, we believe that space is for everyone. So, what's your take on that?
Well, obviously, hopefully, have you seen by now? I absolutely agree. Before, space was really for billion-dollar NASA or huge space budgets and really complex involved systems. But now as stuff becomes miniaturized and there's more launch capabilities and everything, and there's more information on the internet, it's more open to people. And I absolutely think that really anyone can and should get involved. With my stuff, I'm doing ion propulsion at home, so I think you know anyone can definitely get involved in it, and I definitely think that everyone should get involved. And that's why I'm open sourcing all of my builds and stuff, is to show people the entire process of not only how I go through this, but also give examples of these systems in a simplified way that others can approach them. And even if you don't build it and test it yourself, you can actually see how it's built and get the basic principles, and then going forward, expand on your own designs, or at least encourage you to think about new ways to do this stuff. So I definitely 100% think that space is for everyone.
Okay, that's really amazing to know. So, so this is the last question on the list here, right? So, out there to all the space enthusiasts and people who are actually trying to step into the space industries, a small message for them.
So I would say, you know, at the end of the day, if you really like it and want to get involved, just dive right in and do it. It's like I said, it's not the case really anymore where you need millions and millions of dollars or even advanced degrees to get in and involved and start exploring. I just have a bachelor's myself. I certainly don't have a NASA budget. Um, but I think that if you really have a passion for the field, you can definitely contribute. And it definitely helps to share what you do and collaborate with others. I wouldn't be where I am now without collaboration with the community and sharing projects and stuff. And really get your hands dirty, get involved, build some sort of build something. Doesn't even have to be really a rocket or electric propulsion or anything. Get involved with electronics or some small other builds and stuff. And because I think that's the best way to ultimately learn is to really just build stuff. And it doesn't even have to work. Most of my stuff fails. And I've broken a lot of stuff along the way. So I would say don't be afraid to just start building stuff and playing and exploring. That's ultimately, I think, what it's about.
Mm, Um, what's up with the network though?
Right.
Come on.
I can see and hear you fine still.
Yeah, actually, I'm trying to work my audio systems out. The button's a bit jammed. I guess it's not letting me unmute it. What?
All right.
Am I audible?
Yep, I can hear you.
Okay, I don't know. Like it says I'm muted, but I don't know still how I'm audible. Anyways, so it was really an amazing session with you, Mr. Michael. I really enjoyed all of your answers, right? So thanks for sharing your precious time with us, and thanks to the audience as well out there who you guys have been a really good audience.
Yeah, and there's thank you for having me. And if they want, I can actually go through a bunch of the audience questions and answer
Yeah,
all that
absolutely,
stuff because
absolutely.
there's a lot of great questions here. So I'll go through all these and answer. And if you have any more questions, feel free to ask. I'm here for as much time as you need me to, so I'm happy to address whatever. Um, so I believe after the thrust question. Let's see. So Diego Garcia Cacho asked about the test equipment. So for testing, I mean, obviously there's the vacuum chamber, and then, but more than that, um, there has to be ways of actually measuring thrust and certain parameters of the beam and everything. So for the pulse plasma thrusters for measuring thrust, I built a very simple micro pendulum. So it's a little wire with a little Kapton flap at the end, and I aligned that in front of the thruster. And I took video of that deflecting after each shot. And by knowing the mass of the pendulum and the deflection, I can get the thrust from that. For some of the ion beam stuff, there's a very simple there's some simple diagnostics like a Faraday cup, which is literally just a hollow metal cup that collects the beam current. And by looking at the beam current as well as measuring the voltage that's applied to the emitters, I can actually start to characterize thrust and ISP. So some of these systems are very, very simple. Even stuff like Langmuir probes and everything, which I haven't done yet, but they're physically very simple. Actually, for the new piece of instrumentation, the Faraday cup for measuring the ion beam current, quite literally, it is just a copper pipe cap. So I'm literally going to be putting this onto a plastic base in the system with a wire attached to it, leading to a feed through and measuring the current from that. So super, super, super simple. And I've been posting this stuff as well, so you can actually kind of see the progress of that. So even going forward, even more than just the propulsion systems, making them easier, I'm also looking at ways to simplify measurements and readouts. And a lot of times, especially for ion beam physics and everything, you can get away with a lot of measurements with some simple methods. I see a question here from JD Prajapati. Is it worthy to do specialization in aerospace engineering after a bachelor's in electrical? I guess it really depends on what you want to do. I know, at least from friends in the US who have pursued aerospace, when they started out in undergrad, one of the complaints was that you don't really get to start covering any of the useful aerospace stuff until after undergrad. Right, at least in the US, the way that it's set up is a lot of the undergrad aerospace stuff is mostly just mechanical, where you start to touch some stuff in aerospace, but not really as much as getting involved in the master's and PhD programs. So if you really want to pursue aerospace, I would say that it wouldn't hurt to look at that option for the higher degrees as well. But also note that, well, at least from my experience in aerospace, in the US, the aerospace market is very, very competitive. And pretty much all of my friends who have gotten involved with it have had a lot of trouble actually getting into aerospace. One of my friends who graduated a year after me, I think in 2014 or so, just got into his first aerospace company now. So it's been kind of a challenge. And, obviously there's a lot of companies like SpaceX and other launch companies that are popping up that have a lot of positions. But aerospace in general can kind of be, at least in the US, not as widely open as like for electrical engineering, you can get into anything. You can apply electrical engineering to aerospace. I even was an electrical engineer for a civil engineering lab for earthquake engineering. So you can really apply that to a lot of areas. So it really depends on what you want to do and study. So Bhuvan Bagwe asks about if we are close to boosters for these types of propulsion systems. So for electric propulsion, obviously one of the issues is the very low thrust. So these are really useful for very long burning maneuvers. There are actual companies that are looking at transport with using electric propulsion. So there is a big company now, I forget the name off the top of my head, but they're actually building satellite transport units using water-based RF plasma. So they actually have a very huge system which the satellites would be loaded up onto, and they would transport them to higher orbits. So for transfer stages and for deeper stuff, certainly I think there is definitely interest in applications regarding that. Shrisha Madhu asks about space plasma. Can it be used for propulsion? That's a good question, because obviously there is a very weak diffuse plasma, especially around low Earth orbit and other areas. I'm not sure about that. That's actually a good question, because obviously you can use like solar sails and stuff with particles streaming from the sun and everywhere. But actually, I don't know the answer to that. That might be something definitely worth looking into and something interesting to be explored. So let's see. Going down. Ojas Patel is asking about the website link. So I don't know if I can actually enter the chat or post stuff to the public chat. Yeah, I'm not sure if I can actually post things to the chat. But if you want, I'm sure the organizers could forward my information along. So there's the Applied Ion Systems um, website, and then there's also the Twitter, the Instagram, the YouTube, and LinkedIn. So if you want, anyone can feel free to look me up after and send me a message on that if you want more information, or my email is also on the website too. So I'm always open to just chatting with people and um, and help mentoring students and providing answers on electric propulsion. So I can't seem to add the actual link to the chat myself, um, but
Am I
um,
audible? Mr. Michael?
yes,
Yeah, so I was saying that after the session ends, you can add that to website because right now you won't be able to do it. That's some sort of
okay,
like the B Live platform doesn't allow you to do that. So I guess after the session's over, you can do it. Right.
okay, great.
So I guess more or less all the questions were answered.
Yeah. Let's see, a couple more here. Um, so Swapnil Parekh asks about how we can increase thrust for ion propulsion. And for ion propulsion in particular, it's again all goes back to how much power you have. Um, Really, the more power you have for propulsion, the more um, output you can get. So really, for small systems, you're ultimately limited by the physics of the technology itself. And really, to get much higher thrust, you need essentially much larger thrusters. Different ion thrusters will have different thrust to power ratios. So the liquid metal thrusters, the ionic salt thrusters, the traditional um, gas-based ion thrusters will all have different parameters based on the technology. Um, and then Manev Patel asks about what propellant for creating a plasma. So plasma thrusters can really be run on essentially anything. I mean, there are plasma thrusters that use solid metal fuel. There's plasma thrusters that can use water, gas. The pulse plasma thrusters use Teflon, but I've seen lots of other plastics, sulfur. So really, plasma thrusters are very nice that you can use essentially anything for the fuel. It really just depends on the what type of technology. If it's an ablative pulse plasma thruster or if it's a continuous RF thruster. But all different types of fuel options are available. And Sunny asks if I get scolded by anyone to build stuff at home. So as a kid, yeah, I always made a mess. My parents were always telling me I was going to burn the house down with high voltage stuff. I did play with some small hybrid rockets in the base garage at home. So simple hardware with an oxygen tank and some plastic fuel. So that was a little bit sketchy. Here now, I'm still pretty bad with my messes. My wife is incredibly supportive and patient with all of my efforts and me leaving my messes everywhere and um, with all that stuff. So I'm very thankful for her putting up with this stuff all at home. So
Okay, so I guess now all the questions are finally answered, right? I would. Am I audible?
yep,
Hello.
yep, I can hear you.
Okay, cool. So okay, so thank you, Mr. Michael, for sparing your time with us, and it has been really amazing session with you having the talks on the big electric propulsion, plasma, and ion propulsion. It was really an amazing session. I enjoyed it a lot, and I know that the audience as well enjoyed it a lot as well. So, well, thank you guys. You have been a really good audience, and thank you, Michael, too.
No, thank you very much. Yeah, you and the audience have been great, and there have been some really great questions and discussions. So again, if anyone wants to continue discussions or anything, feel free to reach out to me. And again, thank you very much for having me. This has been a really amazing experience, and I really appreciate it.
Thanks a lot.